Hi, you look like you have seen something very scary. Oh, integration. Don't worry, we'll be just learning tiny bit of integration today, which will be applicable for the next derivation that we are going to do. Alright, and in subsequent chapters later we'll see every topic or some of the topics, not every, don't worry, that are required of integration for us to learn. Alright, so let's understand what is the little tiny bit of integration that we need to know for the present chapter 2. If you remember, in differentiation, we have got a formula that if we have a derivative of x raised to the power n, derivative of x raised to the power n, what we get, I hope you remember, it was nx raised to the power n minus 1. So basically what happens here, the power comes to the front and after differentiation, the power here reduces by 1. Because in differentiation, you know, as I told you earlier in class 11, we break up the problem into small parts, alright? But in integration, what we do? We add up all the small parts to get back the original larger problem, right? So if we have now an integration of x raised to the power n, so this is the symbol for integration, like a snake, scary, as integration is. So here integration of x raised to power n, it is given by n x, sorry, it will be x raised to the power n plus 1 by n plus 1. So here the power increases by 1, so it is n plus 1, alright. And also the new quantity x raised to the power n plus 1 is divided by n plus 1 again, okay. So whatever is the number n, it can be 1, 2, 3 and so on. So we have this kind of a formula in case of integration of x raised to the power n, but here I forgot something, we need a dx here. Okay, so basically this small dx that you are adding it up. Okay, sometimes depending on the function that you have there, you can have some power of x like x raised to the power n, or you can sometimes have trigonometric functions sin x, cos x. So these things we'll be learning in subsequent chapters, but for this chapter we only need to know this formula, integration of x raised to the power n dx, which is given by x raised to the power n plus 1 by n plus 1. So to get comfortable with this formula, let us do two numericals based on this and then we'll move on to the part of physics which we need for to understanding electric potential. So let's take our first problem. Say we need to integrate a function y which is defined as say x cube. Okay, let's take y equal to x cube and we have to find integration of y dx. So we have to integrate this function y along small elements dx, alright. So here we'll be putting in integration x cube dx, right? And as we saw in the formula that here the power is increased by 1, right? And on the denominator we'll have a n plus 1. So in this specific example, what we had in the formula as x raised to the power n dx equals to x raised to the power n plus 1 by n plus 1. In this problem n is equal to 3, right? So here we are getting that the value of n in this formula, what we have here, that is equal to 3. So we'll get x raised to the power 3 plus 1 by 3 plus 1. So this will be x raised to the power 4 divided by 4. So that is our answer. Quite simple, right? So let's see one more example here. The specific case we'll be needing in our present chapter. So let's solve for say y equal to x raised to the power minus 2, or you can write this as 1 by x squared, right? X raised to the power minus 2 or 1 by x squared, they mean the same thing. So here if we find integration of y dx, so we have integration of 1 by x squared dx, so it is integration of x raised to the power minus 2 dx. Now say here whatever be the power of x, negative or positive, the formula remains the same. Here you have to increase the power by 1, n plus 1 it was. So here we will find x raised to the power minus 2 plus 1 by minus 2 plus 1. Okay. So minus 2 plus 1 will be minus 1. So we'll get x raised to the minus 1 by a minus 1, or this we can write as negative of 1 by x. Okay, so it will be minus 1 by x that we get. So this is the exact kind of integration that we'll be needing for discussing electrostatic potential. But there will be some boundary conditions there. What it is, I will tell you in that topic. So you may here pause the video and note down these things, then resume it back. Alright, so I hope you have noted down the things. So as you have noticed the topic, we'll be discussing in this video about, as the heading says, electrostatic potential due to a point charge. So we'll be finding the electrostatic potential due to a single point charge. Okay, how to calculate. And as per our earlier discussion, what is electrostatic potential at any point? So as we defined, and you have seen in the definition earlier, that it is the work done in bringing a unit positive charge from infinity to the point where we need to find the electrostatic potential. Okay, so this is how we define it in physics. All right, scientists chose this definition. There is no hard and fast rule or no law in nature that told us to define electrostatic potential like this. We chose to define it that way. So as you can see in this diagram, here we have a source charge capital Q, alright, and we intend to find the electric potential at this point P, which is say r distance away from the source charge. And to find the electrostatic potential at P, how will you find it out? We will find it out as the amount of work done in bringing a unit positive charge, this plus 1 coulomb charge, as you can see, from where? From infinity to the point P. Okay, so that is what this has been mentioned here. Now, in the last part, what we are doing, say when the journey of the unit positive charge is happening from infinity to P at a constant velocity, and also the velocity should be very, very small. Okay, why constant? Because if velocity is not constant, there will be acceleration, and in case of accelerated charged particles, we get electromagnetic radiations coming out of it. So the problem will become more complicated in that case. Alright. So that is why, for the sake of simplicity, and as the name of the chapter says, electrostatic, right? So we want our charges to be in static condition. So that is why, to consider this charged particle to be static in a small interval of time, just like when you look at the sun in the sky, you don't see the sun moving, although we know that it is moving throughout the day from east to west, but we don't see it moving. Suppose when you are looking for 1 minute or 2 minutes, right? So for a small span of time, the sun appears to be stationary because it is moving very slowly. Similarly, if this charged particle is moving very slowly for a small interval of time, while we are studying the problem of the interaction, we can take it to be stationary here. Alright, so that is an important point in this case. So we are imagining, say during its journey, say it has reached a point here, and at this point the distance of the unit positive charge from the source charge we are taking as x. So this black length is x that we are taking right now. Okay, so then at the separation of x, if we find their force of interaction as per Coulomb's law, the force, the electric force will be 1 by 4 pi epsilon naught q1 q2 by r square, right? Okay, by the way, by mistake I wrote here r, so kindly correct this as x square, because right now we are talking about the distance x, right? So please correct this as x square. Alright, because now the distance right now at this location, the distance is x, so we should be taking x square here. Okay, so that's how we can find the force. Now how will you find the work done? So of course it is not possible to measure in one go the entire work done from infinity to a point. So that is why we'll be taking a small length or a small displacement dx, and first let's find how much will be the work done for this small displacement dx. Let's see that. So work done in moving the unit positive charge plus 1 coulomb by dx, a very small displacement dx. Now if the displacement is small, the work done will also be small, right? So let's write the work done is dw, and I hope you remember from class 11 that how we define work done. It is the dot product of force and displacement. So here we'll get f dot dx. Okay, so that is the scenario here. Now if you expand it, we'll get f dx. We get cos theta generally in dot product. I hope you remember, because you see the resultant of a dot product is a scalar quantity, and as we have discussed earlier, work done or electrostatic potential, potential energy, all these quantities are scalar quantities. They don't have any definite direction. Now what will be the angle here? So if you pay attention here, you see the displacement of the particle is happening towards the point P. So from infinity, it is coming in this direction, towards Q, right? But the electrostatic force on the unit positive charge, will it be attractive or repulsive? Yes, it will be repulsive, right? Because both are positive charges. Here there is no minus sign, so means it is a positive charge. This is also a positive charge. So in this case, this electrostatic force F that we have, F will be acting in this direction. It is trying to repel it, right? But our charged particle is moving in the opposite direction. And here you may think, if force is in the opposite direction, why is the charged particle coming in this direction? Because here we are applying some external force, right? So as discussed, in this case, when the charged particle is moving, the applied force and the external force are equal to each other, so that net acceleration is zero in this case. All right. So we are moving because with an external force. That's why you see energy will be getting accumulated, as we are going to see at the end. So basically, here when we talk about the electric force and a displacement, they are mutually opposite to each other. Displacement is happening towards Q, the source charge. Force is acting away from the source charge. Okay. So the angle here will be 180, and cos 180 is -1. So we'll get minus, and F we have got just now is Q by 4 pi epsilon naught x squared times dx. Okay, so that is the small work done dw in moving the unit positive charge by a small displacement dx. Now let's see what will happen if we calculate the total work done from infinity to the point P, which is r distance away. So in this case now we have to do integration, because the entire journey we can divide it into small dx, right? So if we know what is the work done in one such dx, one such element. So to find the total work done, you have to add up the work done in all these small element dx, right? So suppose in this displacement work done is 10 joules. So 10 plus 10 plus 10, you have to add all the values to get the total work done. But since we are taking an infinitesimally small element, the number of such dx will be infinite. Okay, it will be very large continuous values. So in such case, we cannot add them distinctly one by one. We have to use integration in this case. So let's see how to proceed. So this is the expression for dw. So then, total work done in bringing the unit positive charge from infinity to P. This total work done, W, we have to integrate all these small dw, we have to add them up through integration, because these are continuous values, they are not discrete. For continuous values, we use integration, not summation. So we can write integration of f dx. Alright, so that is how we found dw equal to f dx, and we have already found this equation, right? So let me write it directly only. What did we get earlier? It was minus q by 4 pi epsilon naught x squared times dx. Okay, so we are integrating along the small displacement dx. But here you see, as I told you earlier while discussing the general mathematical integration, that here we will be getting something called the boundary conditions. What are the boundary conditions here? See, our integration is not going to happen forever or for the entire length. It is starting from somewhere and it will be ending at somewhere, right? So from where we'll be starting to add up the things, we'll be starting from infinity, because the particle is coming from infinity, right? So the lower limit or the lower boundary of our integration is starting at infinity. Okay, that is what we call the lower limit of integration, or the initial boundary. So it is starting at infinity, which will be given below the integration sign. Okay, and where our integration will be ending, the final boundary. The final boundary is at the point P. And what is the distance to the point P? R. So our upper limit or the final boundary of our integration will be at a distance R. So our integration, the dx, the displacement that we are adding, this addition will start from a distance of infinity from where our particle is coming, and this integration will end at a distance of r, means at the point P. So this is what we call the lower limit of integration, and this is what we call the upper limit. Okay? This is the initial boundary and it is the final boundary. Depending, so it is the lower limit, and this r is what we call the upper limit. Okay, so that you should know the basic things. Alright. So now in integration, just like when we add up the things, the constant terms we can take them common. In differentiation also, if you remember, if we have a constant like d dx of 5x, we take the 5 outside, right? Same here also, whatever constant terms we are having, we can take them all outside the integration. Say here, the x, the distance is changing, right, as the particle is coming down. But q, 4 pi, epsilon naught, these are all constants, so we can take them out of the integration. So we can write here so minus q by 4 pi epsilon naught will come outward here. Okay. So and inside we have integration of infinity to r. The r is not coming on the screen. Let me write it below. So integration infinity to r. There was a minus sign here. So here we have 1 by x squared dx. And we have already seen how to solve this 1 by x squared dx, right? So we'll get minus q by 4 pi epsilon naught. You can write this as x raised to the power minus 2 dx, limit infinity to r. So minus 2 will become minus 1 by minus 1, right? X raised to the power minus 2 plus 1 by minus 2 plus 1. And these limits will be writing on the side with square brackets as infinity to r. Later we are going to use them. I will show you how. So here we'll get a minus 1, this here will get a minus 1. So we have minus q by 4 pi epsilon naught x raised to the power minus 1 divided by minus 1 infinity to r. Now we can take this minus 1 outside because it is a constant again, right? So this minus and this minus will become a plus, as you can see, and x raised to the power minus 1 we can write as 1 by x. Correct? So this is the expression that we get. Now what about the limits? So now we are going to substitute the limits in this function 1 by x, alright? So first always the upper limit. Who is the upper limit here? R minus the lower limit. So in place of x, first we are going to put the upper limit, which will be r. So we get a 1 by r minus upper limit, subtract the lower limit value. Lower limit is infinity, so in place of x we have to put infinity here. Alright. Now 1 by infinity is 0, so we will get q by 4 pi epsilon naught 1 by r. Okay. But you see, as per definition, this work done that we have found in bringing the unit positive charge from infinity to a distance r, this is what we call the electrostatic potential, right? So by definition, electrostatic potential at P will be, so this electrostatic potential P at P will be V, that is equal to the work done, and work done we have got exactly as this expression. This is W we have got, so we can write therefore that V is equal to 1 by 4 pi epsilon naught Q by R. So this is the expression by which we measure electrostatic potential due to a source charge at any distance r away from it. Okay. So I hope you have learned how to calculate electrostatic potential at a point, the derivation here, entire thing. Alright. So in the class we'll be continuing from this point. We'll discuss a few cases and then see what will happen if we have more than one charged particle in a certain region of space and how to find the net electrostatic potential due to time. Thank you.